Peter Molnar, a scientist with a very dynamic research interest. Currently working in climate and environmental sciences, Peter's early career works as a seismologist made significant contribution to the advancement of plate tectonics. Today, he is going to blend in his initial and present research ventures to present us with an interesting story linking plate tectonics and ice ages. Without further ado, please let us welcome Peter Molnar.
Thank you. I was asked in the beginning to talk about what I'm really interested in, which is ice ages, plate tectonics, and stuff like that. But then, because I once was a seismologist, and I also am a ringer here, I'm from Vermont. Well, I spent 2 years as a postdoc here, but the students asked that I talk a little bit about earthquake seismology back in the 60s. So I'm going to take you through earthquake seismology in the 60s rather quickly, then I'm going to thread a needle to get myself to what I'm interested in, and I'll try to do that quickly. So, in the fall of 1966, Lynn Sykes gave a talk on a Monday night. I can tell you that it was a Monday night, and it was either late September, early October, where he described work he had done studying earthquakes along mid-ocean ridges. So in this case, here's Africa, here's South America, this is the Mid-Atlantic Ridge. And he was testing Tuzo-Wilson's transform fault idea. He knew that the earthquakes occurred in the transform fault section of the fracture zone. So for instance, the Romanch fracture zone in here. He knew the earthquakes were in between the two ridge crests and not on the outside. So he knew Wilson's idea passed one test. But when he saw the magnetic anomalies and saw the C4 stratum looked sensible, dropped everything he was doing, and set off to do this. I should say that was so memorable that one of my life's greatest dreams was to find a problem that I could drop everything else I was doing and go work on it. It took a long time to get there, but it was a dream. So he demonstrated clearly that the sense of motion on the transform faults was consistent with transform faulting. I, sitting in the audience, thought, oh my God, continental drift is right. You know, that's kind of like waking up in November in 2016. So it was a jolt. Now, concurrently, Jack Oliver and Brian Isaacs were working on earthquakes in the Tonga region. They had deployed a network of seismograph stations out there, and they no sooner they have seismograms, they observed something strange. So the Tonga region, here's Fiji Island, Tonga, they put 4 seismographs out here, hardly a network by modern terms. Here's Australia, New Zealand. And in cross-section, they had a station on Fiji, on Tonga, a couple more stations. At Fiji, they observed what everybody knew. S-waves are highly attenuated. The S-wave signal was weak on short-period seismographs. No surprise. From deep earthquakes here, from deep earthquakes farther away, even at Tonga, low frequencies. But when the path went up the seismic zone, this thing is meant to mark the seismic zone, the S-waves had very high frequencies. This knocked them over. They were observation seismologists, accustomed to working with data. Perhaps not thinking much about ideas. But they realized that this has to be a high Q zone. High Q means low attenuation. Low Q means high attenuation. Low Q, these hemispheres, low Q, this has been known. This was no surprise. So they said there must be a window of high Q through here, and then they realized that they'd seen other situations where propagation through the lithosphere was low attenuation. They said, well, we subducted down into here. They followed that the next year with a paper. Roger Anderson showed this yesterday. I added something this morning. The authors were determined by lot. It happened to turn out alphabetically. And I think those of us who know this field well would agree that the most important part was written actually by Isaacs, by accident. This was where the big new subduction zone material was presented. Sykes summarized transform faulting, Oliver summarized other things. Well, there I was a student when this was happening, and my thesis consisted of 3 papers, one with each of, guess who? One with Jack Oliver. He was officially my advisor. First paper I wrote, maybe it was written with him. And Jack could never end an exam or a conversation almost with, we've done what you've done, what's the next most important problem? I spent my entire time, and literally preparing for my thesis defense, figuring out how to answer this question. That's where my attention went. I didn't do anything else. And of course, I came in with an answer, and I don't remember what the answer was. I can assure you it was not a good answer. I dropped the topic within 2 years and moved on to something else. But this is what I do. I wake up in the morning, and if I've slept well, this is what I do. Lynn, second paper was with Lynn. Lynn was always asking, how can you test that idea? He had done this with transfer and faulting. This was his way of doing things. And let me, after yesterday, a little focus on that word, because you all heard yesterday that Xavier, of all people, the turncoat. So the scripts had the ideas and Lamont had the data. Well, actually, at Lamont, Jack Oliver's view of a good idea was something you did. It wasn't something that eventually your ego got tied up with. It wasn't something that wasn't an Oliver or whatever. It's something you went out and did. Sykes, he didn't care whose idea this was. If it was a good idea, it was worth testing. You went out and tested it. So the attitude seemed to be, and maybe I have 2,160 hindsight on this, I'm not sure. But we weren't focused on ideas of the kind that egos get attached to. And Brian, I don't think he ever said this, but Brian was the careful one, at least with me. I know this well because I was reprimanded for being sloppy, and Brian is the gentlest guy in the world, so for Brian to reprimand you, you really had to do it bad. Okay, so one last thing about these three guys. Working with them was great. If those of you who are students, I had 3 advisors. That's 3 times as good as one. I encourage it strongly. Work with as many people as you can. You learn more by doing it that way. All 3 of these changed direction. Jack, in the early 70s, turned to CoCorp. This is the Continental Reflection Program. He thought the lower crust is terra incognita. He wanted to study that. He thought that was important. Lynn turned to earthquake prediction. He continues to pursue this. He always argued that earthquake prediction in the 70s was like continental drift in the 50s. There was plenty there, enough to know it was a good problem, but it wasn't yet clear. And he continues. And he recently published a book on nuclear explosion identifying navigation and discrimination. He considered pursue these. So you could say it's both continued seismology, but very different seismology. Brian ultimately turned to surface topography and geomorphology. So there it was. Plate tectonics was done in the 70s. Been there, done that in some sense. What next? Well, it was obvious it was a continent. And Dan McKinsey had already laid claim to half the continental region, all the way from the whole Mediterranean area, all the way to Iran. So Paul Tappamy and I took the rest. And this is, if you don't recognize this, is India down here, the Himalaya coming across over here. So now let's move forward, because I really want to get to climate. Continental geodynamics, for me, became studying active mountain ranges. And the big ones, Himalaya, Tibetan Plateau, Tian Shan, and the Andes. And I had to slip one picture in here. Just very nice. Okay, well, let's fast forward up to the late 80s. And I was tired of this. Geologists claiming that their favorite mountain range around the world rose in Quaternion time. So I wrote a spoof. Rise of mountain ranges and the evolution of humans, a causal relation. and I just thought it was too fun. What the hell? It was rejected 5 times. But let me give you a little bit more. Here's an example. This is a plot, age going back 10 million years. V is what the author called uplift rate. We'll let you figure out. And you see that it's getting high, millimeters a year, increasing exponentially. Again, the same thing for the Cordillera Oriental in the Bolivian Andes. Over here, Shuren, eminent Chinese paleobotanist, elevation, and again, accelerated uplift. That's the word. Now, let me just warn you, if you believe this, we need to talk after this talk, because I got something you might want to buy. And I'll offer you a good price for it. But how did I sell this and fail until finally get it published? Well, I went to the library and collected data on rain sizes of continents. This is the technical term is cranial capacity, by the way. You take these skulls and you fill them up with water. And the green are Homo, the blue and the red are Australopithecus. When I did this back in 1990, the differentiate between the robust and the gracile form, and I won't go any further. You can see an accelerated view going up here. And I will say there was one night where I did not sleep because I was saying to myself, what's the next most important problem? Well, the evolution of humans is the most important problem. What if I'm right? This was part of the reason I had trouble getting the paper published, is reviewers thought that I was serious. Anyway. So, it became clear with this struggle that there was a problem. In fact, a global problem. Geologists claim their favorite mountain range, wherever in the world, rose in ocean over time. Well, that global problem needs a global solution, and climate change was the obvious solution. So that led me in Philip England to write a paper that had a title that was really catchy. It's completely misleading, as it turns out. But I copied the last paragraph of the abstract here. An alternative cause of these phenomena, the phenomena are these, the observations that were used to infer late Cenozoic uplift is late Cenozoic climate change towards lower temperatures. Well, plants that lived at high elevation moved down instead of the mountains moving up, as had been inferred. Increased alpine glaciation was accelerate glaciation. We didn't have much alpine glaciation until the Earth cooled up. A stormier climate, this is a bit of a stretch, but a steeper Boulder equator temperature gradient will enhance baroclinic instability, and you'll get very storm, and so forth. And I pursued this for a while. I had stopped pursuing this mostly because I don't know how to test it. You know? I have my ideas, but I don't know where to go. But this did lead to ice ages. How did we get here? So I'm now changing to the scientific part of this talk. This is a classic plot that Jim Zagos and his colleagues put together 20 years ago or so. Oxygen isotopes from benthic are increasing down here. So increasing means either colder, because of the way the forehands do this, or more ice on land, because ice takes oxygen 16 with it when it builds on land. And you see this pattern going down, and we are up here today, the last ice age is down there, the penultimate is here, going back. The first ice age, most of you know, is here, but if you didn't know that, you might not guess that's where it is. Now, let me digress for a second, because El Nino is important, and one of the greats of El Nino, George Philander, likes to say, ice is really incidental to the ice ages. This, of course, gets the ire of glaciologists, but his point is, if you smooth through this oscillating forehand data, this is with a 200,000 year Gaussian window, you see a steady decline. A steady decline which suggests the Earth is cooling off and cooling off smoothly. This makes it look like a geological question. There's an instability, obviously, when you freeze, you get ice. So some of these big drops due to making ice are a result of instability. And obviously Milankovitch is fundamental here. But what took us from before Milankovitch really started writing X-ages here. What took us before there and stayed us down? That's the question that I want to ask. Okay, we're going to get to El Nino. This is now teleconnections during El Nino. The red showing warm in Canada. Canada gets warm during El Nino. And where I'm going to go with this I'm not the only one who says this, is we had an El Nino like Eastern Tropical Pacific back 4 million years ago. So you recognize some others. India gets dry during El Nino. The worst of famines in India have come during El Nino. You get dry over in Indonesia and so forth. So what's the difference in terms of the ocean? Today, this is the way the ocean looks most of the time, an average annual condition. Warm in the west, warm temperatures here getting to 28 to 30 degrees Celsius out here in what's called the warm pool, and over the oceans in Indonesia. That'll come. A cold time reaching out here in this area. During El Nino, propagandist example, this is the biggest El Nino and the peak of that. But warm all the way across, essentially no zonal temperature gradient at all. So the eastern part gets warmer by many degrees Celsius, and this eastern warming then leads to the teleconnections that make Canada warm during El Nino. Well, let's look at a paleo record. This is from Eastern Tropical Pacific, Pure Lawrence's work. Going back in time, 1, 2, 3, 4, 5 million years. Don't worry about the ice isotopes. This is the temperature based on alkaline saturation index. 4 million years ago, temperature in the east, order 26 degrees today in the east, or 22 degrees, about a 1 degree C cooling over the past 4 million years. That core is this core right out here. Today, it's cool out of here, order 22 degrees. Back here, it's warm, something like what happens during El Nino out in here. And more recent work by Christine Riddell and their colleagues, with many more examples, many more studies in this area. In fact, this is 10 years old, or yet more. It definitely was warmer in the Eastern Pacific 4 million years ago than it is today. I don't think there's much doubt about that. Okay, so here we are. Imagine a world. Imagine a world. I was in the 60s, the Beatles did this. With a permanent average El Nino Eastern Equatorial-Pacific temperature distribution, by analogy with El Nino teleconnections, the atmosphere, we transfer the heat to the high latitudes. Greater warmth in Canada would melt the winter snow and prevent ice sheets from growing. This is the essence of Milankovitch, ignoring the orbits. Milankovitch just said, if it gets too warm in the summer, you melt all the snow, you won't build an ice age. The way to build an ice age or build an ice sheet is by allowing the winter snow to stay there. So this would prevent it, because it would be warm up in that area. So the question then becomes, what geologic process transformed the Eastern Tropical Pacific from El Nino, like this situation, to La Nina, like that situation? And to remind you, the El Nino part, the winds are a crucial part of this. These are two cartoons, normal conditions, La Nina-like, El Nino-like conditions. You have rain over the west, over the islands of Indonesia, ascent. When you have rainfall, you usually have ascent. You need convergence to have this kind of rainfall. The air rises to the top of the troposphere. You have eastward flow aloft, subsidence in the east, and then westward flow along here. This is called the Walker circulation. It's a strong part of present-day circulation. During El Nino, that breaks down. The locus of convection moves out into the center. The winds weaken. You don't have the strong easterly winds blowing across the tropical Pacific. Well, rainfall is going to be key. This is a map of rainfall with the dark colors showing you high rainfall, up to 10 millimeters per day. You see it over the warm pool. You see it along the intertropical convergence zone. But the big point is it's over continents, South America, it's over Africa, and it's over the islands of Borneo, Sumatra, New Guinea. It's over the islands of this region, the maritime continent. So let's look at that more closely. Work by Sobel. This is looking at the Indonesian area. Here's the northern coast of Australia, New Guinea, Timor, Java, Sumatra, Borneo. And you see the rainfall is really concentrated over the islands. Not over all the islands, Borneo doesn't see that much. A blow-up of Sulawesi, Holland Hera, Western and New Guinea, Ceram, Buru, the islands. And in fact, long ago, 1980, Holland and Keene wrote, the afternoon convection provides a near-perfect map of the region. Every island and mountain region is delineated by one or more cumulonimbus. So rainfall is crucial to this. Now, we can look at that a little further. Remember the water circulation. You have ascent over the maritime continent. It's raining over here. Eastward flow aloft, descent further east, westward flow down below. You can quantify that by simply taking the difference in the eastward flow minus the westward flow. This is negative, so the difference enhances both of those. And regress that against precipitation over the islands. So it's precipitation over these islands. And you get this map. So this map, the red, is 3 millimeters per second wind speed per millimeter per day of rainfall over this area. And this reaches all the way across. In other words, the day-to-day variance or variation in the winds correlates very well with rainfall over the islands, and you can get a sensible regression with this. Now, if you do the same with rain over the warm pool, you don't get anything. The strength of the Walker circulation is not correlated with the amount of rain over the warm pool. Okay, well, it's time to put some plate tectonics into this. This is done by Robert Hall from one of the universities in London. This is an animation. This is millions of years, 36. Australia's moving north. New Guinea's part of it. India's charging into the rest of Asia. The blue is going to be seafloor gets subducted. Green is what's going to be left again. Notice you're filling up the Indonesian region with islands. accumulating islands, and you're doing that in two ways, by moving material in there, but also by, with shortening, you thicken the crust, you make mountains and so forth in that area. And just looking at a map, most of Molnar was submerged, has emerged since 5 million years ago. Boulder, again, same thing since 5 million years ago. Ceylon since 1 million years ago. These mountains, there were mountains there 5 million years ago, but they surely were very low. The crust of shortening started only about 8 million years ago. Again, many islands, Timor emerged just in the last couple of million years. So islands have been coming up in this area. How does that matter? Okay, we're going to talk about the effect of islands on rainfall. This is an animation. This is work of Tim Cronin at MIT. This is a cloud resolving model calculation. So it's a 380 by 380 box. That's the back of the box. This is the front going up into the troposphere. These are clouds. This circular region in the middle is an island. Island in this case is a region of low heat capacity. Starting at local midnight. Sorry, I got to zoom into this. I'm going to start. I find my arrow. Sorry. Here. Sorry. Okay, so starting at midnight, what's happening is the island is cooling off, it's radiating into space, sending out heat at the top, cooling. It's going to cool until about 10 in the morning, then it's going to become hot. Rain all around. There's no diurnal cycle of rainfall, or mild, weak for a diurnal cycle in the region. Now, see, it's getting hot. It's going to get hotter and hotter, getting up to well above 20 degrees C. Now you get rain. The blue is showing it's cold. The downdrafts in the rain is dragging cold air down with it. Cold air spreads out. Back at midnight, we go one more day. Again, you're cooling off, you're radiating down into space. Later in the morning, it's going to get hot again, and then suddenly you get a burst of rainfall over this. Okay, it's just about there. 10 now, it's starting to get hot. The sun is hitting it, beating away on it. Of course, you're causing the heating, it's causing air to rise. You draw moisture in, the moisture rises, the moisture condenses, and then the downdrafts. The logic of what's going on is, logic of what I'm going to tell you, is that you heat the bottom. That's what you want to do with convection. The warm air rises during the day, but when you cool, you merely cool the bottom. So you just cool and you spread out down below. What that does is it heats the upper troposphere. So this is a normalized plot of the difference in air temperature between runs with and without an island. This is the sea surface temperature, slightly cooler with an island, slightly cooler. But the atmosphere is warmer because you set up a background circulation that's stronger than just random, where you're constantly taking heat upward into the upper troposphere. And if you, this is that same plot, if you plot the temperature change in the upper troposphere as a function of island area, so this is 10% island area, 20% island area here. These red dots are the experimental results. And going from 10% to 20%, you get about 1 degree C in the temperature difference in the upper troposphere. Now, your first reaction might be 1 degree C. There's about 1 degree C. You go to Miami, you get warm, and you go to Bruce Land, you go to Woods Hole, you get cold. And that's a much bigger difference than 1 degree C. But in the tropics, where the Coriolis effect is negligible, 1 degree C is a big difference. This is the temperature at 250 millibars, or around 12 kilometers. Over, there's New Guinea, Australia, here's South America, Mexico over here. It's a sizzling minus 40 degrees C up here over this region, but it's only a little bit cooler when you get over here, by about 1 degree C, degree and a half C. So 1 degree C by adding those atoms is a big effect. So how have things changed going back to plate tectonics? This is a map of the maritime continent today: Sumatra, Borneo, Java, Sulawesi, and so forth. This is how it looked 5 million years ago. Most of Halmahera was spread out underwater. Timor definitely was underwater. Most of New Guinea was flooded. This is very plain right now, so you don't have to be deep in sea level very much. Most of New Britain and New Ireland, so forth, a good bit of that. Nearly half of Sumatra were underwater. The difference is we have almost 18% land today, but only about 11%, 12% 5 million years ago. So a big increase in islands. So where are we going? More rain falls on and near islands and over oceans. This is the map from Adam's Oval. More islands should mean more rain. Geologists are always substituting space for time when they can. More rain over islands makes a stronger water circulation. Stronger water circulation, we're acting on winds blowing from west to east. Stronger water circulation makes for a cold tongue over here, colder region in this area. And by El Nino analogy, a colder eastern tropical Pacific means a colder Canada. Colder Canada means you can keep last winter's snow and you can build an ice age. So, I'm arguing plate tectonics and ice ages. Plate tectonics added islands, and then by enhanced water circulation, it enabled ice ages to begin. Now, don't want you to be worried about broken bridges and things like that. Those of us with children know that if you want a straight, honest opinion of things, you ask your kids because they don't mince sweet words. So the other giant of Mark Kane, the giant of El Nino, Mark Kane, his son, Jacob Kane, age 11, back, 30-some years ago, what you do is real. You work on the same problem for years. And the best you can do is an approximate answer. You're not even sure it's real.